At the center of the Milky Way, a single star once reached 7,000 miles per second. Nothing natural moves that fast. Nothing, unless it is being pulled by something far heavier than physics ever intended. Tonight, you are going to follow that pull, not just toward the middle of our galaxy, but toward the quietest and strangest object we have ever confirmed in the cosmos. 30,000 light years from where you're sitting, more than 4 million suns worth of mass is packed into a space smaller than Mercury's orbit. If it behaved like most giants of that scale, the night sky would be scarred with its hunger. You would see flares bright enough to wash out constellations, radio storms rolling across the galaxy, and arcs of hot plasma spiraling like cosmic whirlwinds. But you don't. Instead, you live in a galaxy whose central force barely glows, a giant that almost never eats, a presence so quiet it took humanity over a century to even realize it was there. And that is the mystery that brings you here. Why would a monster of this size go silent? Why would the anchor of the Milky Way act more like a sleeping ember than a roaring engine? Across the universe, other galaxies burn with violent, brilliant cores. Quasars shine billions of light years away. But your galaxy's heart whispers. It flickers. It waits. Tonight, you'll explore the clues scientists followed to uncover this paradox. The radio signals that shouldn't have existed. The infrared images that pierced the dust. The stars that orbited something they could not possibly see. You'll drift through the discoveries that led us from confusion to certainty. From a blank patch of sky to the most powerful object our species has ever mapped. And you'll learn why this silence may matter more than any outburst ever could. For now, just let the pace of the galaxy slow your breathing. Let curiosity do the rest. You are about to approach a place where light bends, time warps, and gravity writes its own rules. And at the center of it all, the monster sleeps. As you move closer to the middle of the Milky Way, you begin to notice how quickly the galaxy thickens around you. The spiral arms fade behind a rising wall of stars, dust, and drifting clouds of gas. The bright, clean lanes of the outer disk give way to something far more crowded, far more chaotic, and far more secretive. This region is called the bulge, and it stretches thousands of light years across, forming a swollen heart of old stars and ancient debris. But for everything it contains, the most striking thing about it is what it hides. For thousands of years, humans looked toward this glowing band in the sky and never suspected what lay behind it. With your own eyes, even on the clearest night, you cannot see more than a wash of starlight and a smear of brightness. The truth is that the bulge is packed with dust. Dense, cold, interstellar dust that swallows visible light completely. Each grain is tiny, smaller than a speck of smoke, but trillions upon trillions of them form a curtain thick enough to block even the brightest light sources behind it. When you look toward the center of the galaxy with visible light, you are staring at a wall. This is why, for most of human history, we didn't just misunderstand the center of the Milky Way. We misunderstood our place inside it. Early astronomers believed the sun sat near the middle. The stars seemed evenly distributed across the sky, so it felt natural to assume Earth occupied a central position. It was a mistake born not from arrogance, but from blindness. We were looking through a fog so dense it erased entire structures from view. The bulge contains layer upon layer of dust clouds, each spanning hundreds of light years, stacked like dark sheets draped across a lantern. Light from the galactic center tries to break through, but even the brightest stars are smothered long before their rays reach Earth. The core itself disappears behind thousands of years of cosmic weather, debris thrown off by dying stars, remnants of collisions, drifting rivers of carbon-rich particles. When you peer straight toward that region, all you see is the surface of a storm you cannot enter. Even leaving Earth didn't solve the problem. From space, with no atmosphere to blur your view, the bulge is still opaque. Visible light cannot pass through that dust. Whether you stand in a backyard, float in orbit, or sit on the moon, the result is the same. You are blind to the most important object in the galaxy. Using the wrong kind of light is like trying to look through a mountain with a flashlight. So astronomers learned to stop asking what their eyes could show them and started asking what the dust could not block. They turned to longer wavelengths, radio and infrared, forms of light that slip through dust like water through cracks in stone. Infrared light can glide past the grains that stop visible light in its tracks, and radio waves sweep through as if the dust weren't there at all. These wavelengths became the keys that unlocked the locked room at the center of the Milky Way. From Earth, everything looked bright and uniform. But through these new eyes, patterns began to emerge. Shapes formed. Movements revealed themselves. The darkness wasn't empty. It was hiding something. Hiding it so well that entire civilizations built their models of the universe around an incorrect center. For nearly 2,000 years, humanity placed itself where it did not belong. All because the galaxy itself kept its deepest secret sealed behind dust. You can imagine the moment this realization struck the scientific world. The object we needed to see was hidden not by distance, not by weakness, but by the galaxy itself. The Milky Way wasn't just difficult to observe. It was protecting something, covering something. A presence so dense it bent the paths of stars, yet so quiet it escaped every early instrument we had ever built. And then one day, something began to break through that darkness. A faint noise, a repeating pattern, static that should not have been there. Carl Jansky heard it first, a whisper woven into radio waves drifting across the sky, repeating every 24 hours as if following the turning of the stars. Something in the sky is making static, and it repeats every day, he said, unaware he had caught the first hint of the monster's breath. That static, that whisper, would become the first clue. You can imagine the scene. A quiet New Jersey field in the early 1930s, a wooden tower rising above the grass, and a young engineer named Carl Jansky turning a strange rotating antenna toward the sky. He wasn't searching for stars. He wasn't hunting for cosmic mysteries. He had been assigned a practical task for Bell Labs: track down sources of static that interfered with radio communications. Airplanes, thunderstorms, sunspots. That was all anyone expected him to find. But one day, buried in the noise, he noticed something different. A faint hiss, steady and soft, that didn't match any weather pattern or earthly signal. It rose and fell as his antenna turned, and then vanished, only to return exactly 24 hours later. And then again, and again. Jansky did what any careful engineer would. He measured it, charted it, waited for it to stop. But it never did. The signal followed the turning of the sky, not the spinning of the earth. It wasn't tied to the human world at all. It was tied to the stars. As days became weeks, he traced its origin to a spot in the constellation Sagittarius, a place long associated with the glowing, dusty heart of the Milky Way. To Jansky, it was simply a strange radio frequency coming from the direction of the galaxy. He had no way of knowing that he was the first human being to ever detect the breath of the monster at the center, a whisper escaping the darkness that swallowed all visible light. But Jansky's antenna wasn't powerful enough to map the source. It could hear, but it couldn't see. So another pioneer stepped forward, an amateur radio enthusiast named Grote Reber. In his backyard, using his own money, he built the first true radio telescope, a curved metal dish that looked like a homemade satellite long before satellites existed. Where Jansky's antenna picked up faint static, Reber's dish carved the sky into patterns. And in those patterns, something stood out. A region in Sagittarius glowed like nothing else. A powerful, compact source of radio waves blasted outward from deep within the galaxy's core. It was stronger than any other point in that entire region of sky. Stronger than star clusters. Stronger than nebulae. Stronger than anything that should have existed behind the thick curtain of dust. And yet, in visible light, it was completely invisible. A source stronger than anything else in Sagittarius, but invisible. Reber labeled it Sagittarius A. He had no idea what it was. No one did. But the signal was unmistakable. Something in the galactic center was generating radio waves with a consistency that made no sense. Not a star, not a supernova remnant, not a cloud of gas. Something compact, something intense, something pushing energy through dust that swallowed everything else. For the first time, humanity wasn't looking at the center of the galaxy. It was listening to it. And what we heard was a whisper that didn't belong to ordinary stars. A whisper that hinted at a mass so great and a force so focused that only one explanation would make sense decades later. For now, though, it was simply a mystery, a question without edges, a clue without a name. The most important part of the discovery is this. Neither Jansky nor Reber knew what they had found. Jansky thought it was an unusual patch of sky noise. Reber suspected some kind of energetic region behind the dust. Neither imagined they were listening to a gravitational giant 4 million suns heavy. Both men heard the center of the galaxy calling, and neither recognized the voice. But the signal persisted, day after day, year after year, constant, patient, waiting for better instruments, better technology, better eyes. Radio waves were the only thing escaping the darkness, and they were telling anyone who cared to listen that something extraordinary was hiding in the heart of the Milky Way. Soon, you will see the monster. But before that could happen, astronomers needed to find a way to look through the dust completely. Not with ears this time, but with a new kind of sight. To understand what was making those radio waves, we needed new eyes. For generations, astronomers had run into the same wall. Visible light simply could not reach them from the center of the Milky Way. No matter how large the telescope, how clear the night, or how dark the sky, the bulge remained a solid curtain. The dust swallowed every wavelength the human eye depends on. What looked like a glowing stripe in the night was, in reality, the surface of something far deeper, far more crowded, and far more violent. To truly see past that barrier, you needed a different kind of vision, one that didn't care about dust at all. Infrared light became that vision. Unlike visible light, it can slip between dust grains and glide through the thickest clouds. It ignores the obstructions that stop starlight cold. Dust that once acted like a wall suddenly behaved like a thin veil, and humanity realized it had been blind only because it was looking with the wrong eyes. When infrared instruments first swept across the sky, the darkness near Sagittarius didn't deepen. It brightened. Patterns began to appear where once there had been nothing but shadow. The first major breakthrough arrived with IRAS, the infrared astronomical satellite. As it scanned the sky, it created a world map of heat, a map of what glowed behind the dust rather than in front of it. For the first time, the galactic center lit up unmistakably, not just as a patch of brightness, but as a concentrated region bursting with energy, structure, and motion. It was like someone had traced a line through the fog and revealed a lantern underneath. The core was not quiet. It was burning. Then came Spitzer, a far more advanced infrared observatory. It refined what IRAS had hinted at, sharpening the center into detail that no human generation had ever seen. The dust clouds no longer hid the story. They framed it. Inside them, hot gas churned. Arcs of warm material stretched like ribbons twisted by unseen forces. Even more surprising was the behavior of certain stars. They moved quickly, irregularly, almost as if they were being tossed. In visible light, these stars were ghosts. In infrared, they became unmistakably real and unmistakably disturbed. This was the moment when the first hints of chaos emerged. Infrared images showed stars packed in tight orbits, crowding around something they could not possibly be orbiting unless it was extremely dense. Their paths curved too sharply. Their speeds were too high. Their motions were too wild to be caused by ordinary gravitational tug from a cluster of stars. Something heavy was gripping them. Something compact. Something hidden in the very center. Astronomers began asking a new question. What is forcing these stars to move like this? Infrared light didn't just reveal stars. It revealed their unease. It showed motion where there should have been calm. It showed energy where there should have been equilibrium. The core wasn't just bright. It was restless. A quiet restlessness, like a deep breath being held. The idea spread through the scientific community. Perhaps there was a single object at the center, something massive enough to control the entire region. Infrared images gave the first visual hint that the heart of the Milky Way might not be a crowded field, but a stage on which every actor was orbiting the same invisible point. This was the first time in human history when you could say we were truly looking into the center of our galaxy. Every generation before had stared at a false picture, a flat wash of brightness hiding the very thing they needed to understand. Now, with these longer wavelengths, the ancient dust finally stepped aside, and what emerged behind it felt like a revelation. Civilization had looked through the darkness for the first time, and the darkness blinked back. Reinhard Genzel would later say, "Infrared light opened the door to the galactic center." And that's exactly what it did. It turned centuries of blindness into a single, breathtaking moment of clarity. Behind the swirling dust, behind the crowded stars, behind the glow of the bulge, something enormous was shaping everything around it. The chaos wasn't random, it was gravitational. Infrared light had shown us the stage. But the only way to understand the central force was to watch the actors themselves. The stars performed their orbits. Their motions held the answer. Their paths would reveal the hidden mass. Their dance would point directly to the monster. But seeing the stars wasn't enough. We had to watch how they moved. When the dust finally parted and infrared light revealed the crowded core of the Milky Way, astronomers realized something astonishing. The center of the galaxy was not calm. It was alive with motion. Stars twisted and curved in tight loops, bending their trajectories as if pulled by a force far stronger than anything they had ever encountered. Seeing them was one thing. Understanding their movements was another. And for that, scientists needed decades of patience, precision, and the most exacting measurements ever attempted in astronomy. Two groups stepped into this challenge from opposite sides of the world. One led by Reinhard Genzel, working with the Very Large Telescope in Chile. The other led by Andrea Ghez, using the Keck Observatory in Hawaii. Both teams knew that the key to uncovering the truth about the galactic center would not be found in a single image, but in thousands of images, taken year after year, night after night, tracking every shift in the positions of stars that clustered near Sagittarius A. These stars, later called the S cluster, were the closest objects to the hidden mass, and their orbits carried the fingerprints of whatever held them in place. Among them, one star stood out immediately, S2. It was bright, clean, and fast, incredibly fast. As Genzel and Gies's teams tracked its progress over time, they watched it whip through space at speeds exceeding 5,000 kilometers per second. No natural object in the galaxy moved faster. Nothing even came close. Watching S2 was like watching a planet orbiting in fast forward. Its journey around the center compressed into a mere 16 years. Compared to Earth's leisurely 365-day loop around the Sun, S2's orbit was razor-tight, violently quick, and astonishingly small. Each year, the two research teams added new measurements. Every time S2 completed another fraction of its ellipse, the data sharpened. Points on a graph became a curve. The curve became an orbit. And the orbit became a perfect demonstration of a fundamental truth. Something unimaginably heavy was holding the star in its grip. Using Newton's laws and Einstein's refinements to them, astronomers calculated the mass required to force S2 into such a steep path. The answer was 4 million suns. Not spread out, not diffused. Focused into a region so small that no known physical structure could possibly hold it. This was the moment the process of elimination began. If the object at the galactic center were a cluster of stars, it would tear itself apart under its own gravity. If it were a massive glowing object, we would see its light easily through infrared. If it were a cloud of gas, it would be far too diffuse to pull a star into a 16-year orbit. Every alternative collapsed under basic physics. Only one possibility remained: a supermassive black hole. The only kind of object capable of containing 4 million solar masses in a space smaller than Mercury's orbit. As the years passed, the orbit of S2 became the most meticulously studied loop in the history of astronomy. When the star reached its closest approach, the pericenter, it skimmed past the hidden mass at a distance so small that even a slight deviation should have flung it into chaos. Instead, it followed its predicted path perfectly. The speed, the curvature, the timing, everything aligned with the presence of a black hole. This was not a runaway star, not a scattering event, not a fluke. The stars were not running away. They were orbiting, and suddenly, the entire field of astrophysics shifted. What infrared had hinted at, orbital mechanics confirmed. Sagittarius A was no longer a hypothesis or a rumor buried beneath dust. It was real. It possessed a gravitational pull so concentrated that only a black hole could explain it. And the dance of the S-cluster stars became its signature, a pattern as unmistakable as a heartbeat on a monitor. Andrea Ghez captured the significance of the discovery with a single sentence. We now know, beyond any reasonable doubt, that a supermassive black hole sits at the center of the Milky Way. For the first time in human history, we had evidence that wasn't based on theory, speculation, or indirect clues. This was reality measured in the heavens themselves, a cosmos writing its own proof across the sky. It was a triumph, not loud or dramatic, but quiet and exact. A moment where mathematics became a telescope and gravity revealed the monster behind the dust. But if this was the first glimpse, it was far from the clearest one. To truly see the monster, not just feel its pull, astronomers needed sharper vision still. But to truly see the monster, we had to sharpen our eyes even further. Even after infrared light unlocked the first clear view of the galactic center, one stubborn problem remained. When you look at the sky from Earth, every star seems to shimmer. That gentle twinkling you see on a calm night might look beautiful, but to astronomers, it is a distortion. A reminder that the atmosphere above you is constantly rippling like a sheet of warm air over asphalt. Every layer of moving air bends starlight in a slightly different direction. By the time that light reaches a telescope, the star is no longer a crisp point. It becomes a blur, a smear, a shimmering dot that refuses to hold still. This effect is harmless when you're simply stargazing, but when you're trying to measure the motion of stars orbiting a compact, invisible object at the center of a galaxy, blurring is devastating. Even infrared telescopes, powerful enough to pierce the dust, still had to look through Earth's turbulent atmosphere. And that turbulence softened every star, no matter how long the exposure or how perfect the mirror. To fully understand Sagittarius A, astronomers needed more than better sensors. They needed a way to remove the twinkle from the sky itself. That solution came from one of the most remarkable pieces of technology humanity has ever aimed upward: adaptive optics. The idea sounds like science fiction. Create an artificial star high in the atmosphere and use it as a reference point to correct the sky in real time. Telescopes like Keck and VLT fire a concentrated beam of golden laser light into a layer of sodium atoms about 90 kilometers above Earth's surface. The sodium atoms absorb the laser, glow slightly, and form a tiny bright point in the sky. This point behaves like a star, but unlike real stars, Scientists know exactly how it should look. By watching how this artificial star blurs and wobbles, computers measure the exact disturbances caused by the atmosphere. Then, dozens of times per second, in reality, closer to hundreds, a deformable mirror inside the telescope flexes to cancel out those disturbances. These mirrors shift their shape as fast as 700 times each second, fine-tuning the incoming light and straightening the path of every photon. What arrives at the detector is no longer a smeared, trembling star. It is a pinpoint, sharp, clean, almost perfect. For the astronomers studying the galactic center, the first night with adaptive optics was transformative. Stars that once looked like glowing cotton balls snapped into focus. The S cluster, previously a crowded patch of fuzzy light, resolved into individual stars separated by mere milliarc seconds. S2, the star racing fastest around Sagittarius A, appeared crisp for the first time. Its position could be measured with astonishing precision, allowing researchers to map its movement year after year with accuracy that had been unimaginable only a decade earlier. Suddenly, the dance of the stars wasn't just visible. It was measurable, traceable, and undeniable. The universe didn't need to change. Our tools did. And once they did, the heart of the Milky Way revealed itself with a clarity no astronaut's eye could ever match. What was once hidden beneath atmospheric blur now shone like diamonds against velvet. Adaptive optics became the technology that stole the twinkle back from the sky. It turned the Earth's atmosphere from an obstacle into something predictable, something correctable. With every improvement, astronomers got closer to seeing the exact structure of the orbits around Sagittarius A. They weren't just observing stars anymore. They were reading the gravitational handwriting of the monster itself. Richard Davies summarized the breakthrough perfectly. Adaptive optics changed everything we thought possible from the ground. And for the study of the galactic center, that was not an exaggeration. Without this technology, the evidence for the supermassive black hole would have remained suggestive. With it, the evidence became irrefutable. Now that we could see the stars, we needed to understand what they were orbiting. Before you can understand what makes Sagittarius A so unusual, you need to step back and look at the family it belongs to. Black holes come in different sizes, different origins, and different behaviors. Some are born in explosions. Some grow for billions of years. Some may have existed before the first stars ever formed. And all of them help shape the universe in ways both subtle and staggering. When you place Sagittarius A's alongside its relatives, its quiet nature becomes even more mysterious and far more compelling. The smallest members of this family are stellar mass black holes. These form when massive stars collapse at the end of their lives, their cores imploding under gravity, their outer layers blasted away in supernova explosions. A typical stellar mass black hole weighs between 5 and 100 times the mass of the Sun. They are dense, fierce objects, capable of tearing apart nearby stars and shining brightly in X-rays when they feed. One of the most famous examples is Cygnus X1, a black hole locked in a gravitational dance with a bright blue star. When it pulls matter from its companion, it glows with the fury of an object eating its own neighbor. But not all black holes fit so neatly into the small category. Somewhere between the big and the tiny lies a middle ground, intermediate mass black holes. These weigh anywhere from 1,000 to 100,000 solar masses. They're rare, elusive, and difficult to confirm. For decades, astronomers debated whether they even existed. A few suspects have emerged, often hiding inside dense star clusters or dwarf galaxies, but evidence remains thin. If they do exist in large numbers, they could be the seeds from which supermassive black holes grow. If they don't, then the universe may have forged its giants in a different way entirely. At the top of the scale are the supermassive black holes, the giants anchored at the centers of galaxies. These objects range from 1 million solar masses to tens of billions. They are the engines behind quasars, the gravitational cores that stabilize galaxies, the silent architects of cosmic structure. Unlike stellar mass black holes, they weren't formed from single stars. They grew over time, feeding on gas clouds, merging with other black holes, and guiding the evolution of their entire galactic neighborhoods. Sagittarius A is one of them, though on the smaller side compared to the colossal black holes found in brighter, younger galaxies. At roughly 4 million solar masses, it is modest by supermassive standards, but still powerful enough to dominate the inner light years of the Milky Way. And then, at the speculative edge of theory, sits a fourth category: primordial black holes. These are hypothetical objects that could have formed just after the Big Bang, created not from stars, but from raw fluctuations in the newborn universe. If they exist, they could be as small as mountains or as massive as planets. Some theories suggest they might even make up a portion of dark matter. But to this day, no primordial black hole has ever been confirmed. Their existence remains an open question, a doorway to physics we haven't yet learned how to open. The differences between these categories go beyond mass. The size of a black hole's event horizon, the point of no return, increases with its mass. A stellar mass black hole might have an event horizon only a few miles wide. Sagittarius A, with its 4 million solar masses, has one roughly the size of Mercury's orbit. But because the mass is spread over such a larger region for the giants, their average density can actually be lower than that of their smaller cousins. The largest black holes are paradoxically the least dense, stretching gravity across enormous volumes. This helps explain one of their most surprising traits. Supermassive black holes can appear calm. They aren't always roaring, devouring gas, or generating intense radiation. In fact, they only become violent when they have plentiful fuel. Without material to feed on, they settle into long periods of quiet. A supermassive black hole without an accretion disk is like a dormant volcano, imposing but still. Sagittarius A is one of those quiet giants, not because it lacks power, but because it lacks food. When you compare Sagittarius AI to the tiny, furious stellar mass black holes like Cygnus X1, or to the rare middleweights hiding in nearby galaxies, or to the hypothetical primordial ghosts from the dawn of time, something becomes clear. Sagittarius A does not behave the way a monster is expected to. Not all monsters roar, some barely breathe, and that stillness is what makes it so compelling. Black holes may be the simplest objects the universe ever created, just mass in its purest form. And yet, they remain some of the most complex to understand. As physicist Kip Thorne once said, Black holes are the simplest objects in the universe, and yet the most complex to understand. The more we learn about them, the more the universe seems to widen. But Sagittarius A is not alone. Every galaxy seems to have its own sleeping giant. When you step back from the Milky Way and look across the universe, a remarkable pattern emerges. No matter which direction you turn, no matter which distant island of stars you examine, large galaxies almost always share the same hidden architecture. Spiral galaxies with graceful arms, massive elliptical galaxies glowing like soft lanterns, galaxies colliding, stretching, merging. Beneath all of these shapes lies a common anchor, a supermassive black hole sitting quietly at the center. It doesn't matter whether the galaxy is young or old, bright or dim, ordered or chaotic. The giants are always there. This realization didn't come quickly. It took decades of observing thousands of galaxies for astronomers to understand that the presence of a central black hole wasn't an exception. It was a rule. Every spiral or elliptical galaxy that has been studied in detail carries a black hole in its heart, and the mass of that black hole seems to correlate strongly with the size of the galaxy's central bulge. This tight connection, known as the M-sigma relation, suggests that galaxies and their supermassive black holes grow together, shaping each other through gravity, radiation, and time. At first glance, this might seem backwards. Why would an object that is tiny compared to the whole galaxy have such influence? The Milky Way spans more than 100,000 light-years, yet Sagittarius A's event horizon is no larger than Mercury's orbit. And still, the galaxy's evolution appears to be tied to its mass. The explanation lies in how gas flows through galaxies. Over millions of years, gas drifts inward toward the center, pulled by gravity and cooled by collisions. When this material reaches the inner regions, it can feed the supermassive black hole, triggering periods of intense activity. During these active phases, a galaxy's core becomes a kind of furnace. Gas swirling into the black hole heats up, radiating enormous amounts of energy. These episodes can create what astronomers call active galactic nuclei, blazing central engines that shine brighter than all the stars in the galaxy combined. When this activity becomes powerful enough, the galaxy turns into a quasar, visible from billions of light years away. But this activity also has consequences. Jets and winds from the central engine can blow gas outward, slowing or even shutting down star formation in certain regions. In quieter times, when the black hole isn't feeding heavily, star formation resumes. The black hole becomes a regulator, a cosmic thermostat, controlling how quickly a galaxy builds its stars. Without this regulation, galaxies might burn through their gas too quickly, or collapse irregularly, or form stars in unstable bursts. The supermassive black hole provides balance. It keeps the ecosystem of the galaxy in order. This idea becomes even more intriguing when you imagine a galaxy without a central black hole. Simulations suggest that such galaxies would look different. Their centers less organized, their star formation chaotic, their structure less stable. The black hole's gravity isn't just an anchor, it's a stabilizing force. Without it, the galaxy could drift into disarray. The presence of a supermassive black hole might be one of the reasons galaxies evolve into the elegant shapes we see today. When you look back at the early universe, the connection becomes even clearer. The youngest galaxies we can observe often host quasars, black holes devouring material at furious rates, releasing torrents of light that outshine entire galaxies. These were not quiet giants like Sagittarius A-star. They were raging engines, sculpting their surroundings with radiation and winds so strong they reshaped the flow of gas for millions of years. The Milky Way itself almost certainly went through such a phase, long before Earth formed, long before the Sun existed. The galaxy you live in today feels calm compared to that ancient era. The core is dim. The black hole is quiet. Star formation happens at a measured pace. But the stillness you see now may be the aftermath of earlier storms. Storms that helped sculpt the Milky Way into the spiral beauty it is today. The calm we see today may be the result of ancient violence. As astrophysicist Priyamvada Natarajan put it, supermassive black holes are cosmic engines shaping the galaxies around them. They are more than masses of collapsed matter. They are architects, regulators, and anchors. And though Sagittarius AI is relatively small compared to the behemoths found in distant quasars, it has shaped the Milky Way in profound ways. Its presence is not an accident. It is part of the galaxy's blueprint. But even among giants, Sagittarius A stands out. When you place the Milky Way into the broader landscape of the universe, a humbling shift happens. You realize just how modest our home galaxy really is, a quiet spiral drifting in a cosmos filled with giants far more extreme. Sagittarius A, with its 4 million solar masses, may dominate our own galactic center, but compared to the heaviest black holes ever discovered, it is a lightweight, a small ember among roaring furnaces. Take M87C, for example, the first black hole ever imaged directly. At the heart of the massive elliptical galaxy, M87 lies a black hole more than 6.5 billion times the mass of the Sun. Its event horizon is so large that a beam of light would need an entire day to cross it. In comparison, Sagittarius A is tiny. If M87 Kes sat where SGR A-San is now, its shadow would span nearly the width of the entire solar system. And unlike the quiet giant in our galaxy, M87 Kes powers a jet that shoots thousands of light years into space, a cosmic lighthouse visible even from Earth. And then there are the true monsters, the ones that stretch the limits of imagination. In the galaxy Holm 15A, astronomers found a supermassive black hole estimated at around 40 billion solar masses. Its event horizon would swallow the orbit of Neptune with room to spare. It sits in the center of a galaxy that once merged with several others, growing larger each time, feeding on gas clouds, stars, and even other black holes. Holm 15A's central object is so enormous that it challenges our understanding of how quickly black holes can grow and what ultimately limits their size. But even Holm 15A Query bows before one of the brightest beacons in the universe, the quasar Ton 618. At 66 billion solar masses, it is one of the most luminous objects ever recorded. The light from Ton 618 is brighter than 100,000 entire galaxies combined. Its accretion disk burns with such ferocity that it can be detected from billions of light years away, a relic from a time when the universe was far younger and black holes fed eagerly. Seeing Ton 618 is like looking back into an age when cosmic giants ruled without restraint. Placed beside these titans, Sagittarius AI feels almost delicate. 4 million solar masses is enormous by any ordinary scale, but in the realm of supermassive black holes, it is closer to a seed than a colossus. And yet, this apparent smallness is part of the mystery. The biggest black holes aren't the most puzzling. They behave more predictably because they feed constantly, radiate brightly, and reveal themselves through jets and flares. Sagittarius A does none of this. Its quiet nature makes it harder to observe, harder to understand, and ultimately more intriguing. Size is not the same as danger. A black hole's behavior depends far more on how much material it consumes than how massive it is. The enormous giants in distant quasars are only visible because they are actively feeding, converting falling gas into blazing radiation. Without fuel, even the largest black hole becomes dim. With too much fuel, even a small one becomes fierce. Activity shapes visibility. Activity shapes personality. Sagittarius AI sits in a rare middle ground, too small to shine like a quasar, too quiet to be obvious, yet perfectly positioned for astronomers to study in exquisite detail. It is close enough for us to track individual stars around it, but subdued enough that its environment isn't overwhelmed by violent outbursts. It is small, yes, but the small one is the strangest one. Heino Falca, one of the scientists behind the Event Horizon Telescope, once said, "Black holes come in all sizes, but they play by the same rules. The rules are simple. Mass bends space, and space guides motion. Everything else, the brightness, the flares, the jets, depends on what the black hole has to eat, and that is where the mystery of Sagittarius A deepens. If size isn't the mystery, maybe its hunger is. All your life, you've seen illustrations of black holes as blazing rings. Bright, swirling disks of gas spiraling inward like water down a drain. And for the most part, those images are accurate. When a black hole feeds, even a little, the material around it heats to millions of degrees. It glows in X-rays. It shines in radio waves, and it becomes one of the brightest objects in the universe. Feeding black holes are spectacular, violent, impossible to miss. But Sagittarius A refuses to behave that way. For decades, astronomers expected to find a shining accretion disk around it, a thick band of hot gas marking the boundary between calm space and gravitational collapse. Instead, they found something faint, something thin, something so dim it didn't fit any model of a black hole living at the center of a galaxy like ours. Where there should have been a blazing halo, there was only a whisper of light. This created one of the greatest puzzles in modern astrophysics. How could a black hole weighing 4 million suns be so quiet? Why wasn't it devouring gas from its surroundings the way black holes in other galaxies did? The material was there. Clouds drifting inward, stars shedding mass, dust and plasma swirling through the central region. And yet Sagittarius A seemed to take almost none of it. It was as if it were fasting. Researchers began referring to this as the black hole fasting hypothesis. The idea was simple. Sagittarius A wasn't bright because it wasn't eating. Maybe the gas flowing toward it was too thin, too hot, or too disorganized to form a stable accretion disk. Maybe the black hole's magnetic fields were ejecting most of the incoming material before it could fall in. Or maybe the inner regions of the galaxy had been swept clean long ago, leaving only scraps for the black hole to nibble on. Then came 2014, the year everyone thought the mystery might finally break open. A small cloud of gas named G2 was predicted to pass close to Sagittarius A-star. Astronomers around the world watched in anticipation. If G2 were truly a gas cloud, it would stretch, heat up, and create a dramatic flare as it approached the black hole. Some predicted that Sagittarius A-star might brighten by a factor of 10 or more. It could have been the first time in human history that we witnessed our black hole feeding in real time. But nothing happened. No flare, no brightening, no fireworks. Sagittarius A-star remained as quiet as ever. When the dust settled, literally and figuratively, researchers realized G2 wasn't a pure gas cloud at all. It had a hidden stellar core wrapped in gas and dust, and that core held the cloud together, preventing it from being torn apart. G2 passed the black hole unscathed, and the monster at the center of the Milky Way didn't stir. This deepened the mystery. Why does Sagittarius A ignore nearly everything that comes near it? Years later, the Event Horizon Telescope pointed its global network of radio antennas toward our black hole and captured the first image of its shadow. The results were surprising. Rather than a smooth, flat accretion disk like the one in M87 King, the material swirling around Sagittarius A appeared chaotic, tangled, and disordered. The plasma was extremely hot, but incredibly thin. Too thin to emit strong light, too unstable to form the tight glowing ring seen in distant quasars. Sagittarius A-star wasn't hiding a missing disk. The missing disk was not missing. It's hiding, stretched out, turbulent, and starved of fuel. The black hole was still pulling in material, but the process was so inefficient, so delicate, that most of the energy was carried away rather than radiated outward. It was not a sleeping monster. It was a starving one. This explains why Sagittarius A is so dim, why it cannot compete with quasars, why the center of the Milky Way looks calm compared to the blazing hearts of young galaxies. It isn't that our black hole lacks power, it simply lacks dinner. As Shep Doeleman famously said, Sagittarius A is whispering, not screaming. But even a starving monster can surprise you. It may be quiet most of the time, but it is not dead. Sometimes, the center of the Milky Way flickers. Brief, unpredictable flashes hinting at the turbulent plasma swirling just outside the event horizon. But sometimes, even a starving monster flickers. For all its quiet, Sagittarius A is not completely still. Every so often, without warning, without pattern, something stirs near the event horizon. A sudden spark, a brief flash, a momentary brightening that lasts only minutes before fading back into darkness. These events are called flares, and they are among the most unpredictable signals ever observed from our galaxy's center. Most of the time, Sagittarius A whispers. But during a flare, it speaks. Astronomers first noticed these bursts in X-ray and infrared observations using telescopes like Chandra and the Event Horizon Telescope's monitoring networks. On a typical night, the black hole emits a soft, steady glow. But then, seemingly out of nowhere, the brightness surges. Sometimes by a factor of 10, sometimes by a factor of 100. For a few minutes, the galactic center flickers like a candle in the wind, as if a pulse of energy has escaped from deep near the event horizon. And just as quickly as the flare rises, it dies away. The light collapses, the glow dims, and Sagittarius A returns to its usual silence. What causes these sudden bursts? Astronomers still aren't entirely sure, but three possibilities stand out. One explanation is that a tiny piece of matter, maybe a clump of gas or debris, wanders too close, heats up, and releases a flash of energy as it spirals inward. Another theory involves magnetic reconnection. Tangled magnetic fields near the black hole suddenly snapping into new shapes, releasing intense bursts of heat and radiation. A third idea points to relativistic effects, the strange bending of space and time around the event horizon, magnifying and compressing light in unexpected ways. No matter the cause, the result is unmistakable. A flash that cuts through thousands of light years of dust and arrives at Earth as a brief heartbeat in the darkness. Some flares are so bright that they momentarily outshine everything else in the central region. Others are subtle, detectable only with sensitive instruments tuned to the faintest wavelengths. And in a few rare cases, gravitational lensing, the bending of light by the black hole's own gravity, magnifies the flare even further, stretching it into a shimmering arc that rises and falls like a cosmic echo. To astronomers, these flares feel like the black hole's breath, a reminder that even a starving monster still has a pulse. They are the moments when a quiet giant reveals just enough of its power to make you lean closer, to listen more carefully, to imagine the turbulence hidden beneath the calm. If you were to chart the brightness of Sagittarius A over time, the graph would look almost like a heartbeat, long periods of steady quiet interrupted by brief sharp spikes. It is not a rhythmic pulse, not predictable, but unmistakably alive. As Daniel Wang once said, every flare is a message, even if we don't yet understand the language. And that captures the feeling perfectly. Each flare seems to carry information, clues about the plasma swirling near the event horizon, about the geometry of space-time around the black hole, about the way matter behaves under the most extreme conditions in the universe. And yet, each flare remains just beyond full explanation, a riddle written in light. What makes these bursts even more fascinating is their contrast with Sagittarius A's overall demeanor. The black hole is quiet 99% of the time. It barely feeds, barely emits, barely moves. But the quiet heart still pulses. And those pulses provide some of the best opportunities we have to glimpse the physics operating at the threshold of the unknown. As you imagine the center of the Milky Way, still, dark, wrapped in dust, picture one sudden flare illuminating the region like a spark inside a storm cloud. Brief, brilliant, gone. A reminder that beneath the calm exterior lies a force capable of shaping the entire galaxy. And gravity itself helps us hear that message more clearly. As you move closer in your mind to the region just outside Sagittarius A, something extraordinary begins to happen. Something that defies everyday intuition, but flows naturally from the laws of the universe. Light, which normally travels in straight lines, no longer behaves the way you expect. Instead of moving past the black hole untouched, it bends. Space curves around the mass, and light follows that curve, wrapping itself into shapes your eyes were never designed to see. This phenomenon is called gravitational lensing, and it is one of the most beautiful effects predicted by general relativity. In a sense, the black hole becomes a kind of magnifying glass, not because it produces light, but because it shapes the paths that light takes. When a star or cloud passes behind Sagittarius A, The black hole's gravity warps the incoming light, pulling it into arcs, halos, or mirrored images. Sometimes the light splits, taking more than one possible route around the black hole. One path may be longer than the other, so the signals arrive at slightly different times. A cosmic echo created not by sound, but by curved space. Even though the source behind the black hole is unchanged, the light that reaches you is altered, stretched, magnified, or even duplicated. This effect is subtle in everyday life, but near a supermassive black hole, it becomes profound. Lensing can brighten objects that would otherwise be too faint to detect. It can reveal gas streams that hide just behind the event horizon. It can amplify flares in ways that help astronomers measure how close they originate to the edge of the black hole's shadow. In rare moments, it even acts like a natural zoom lens, giving scientists glimpses of the plasma swirling in the innermost regions, the very edge where space and time begin to fall inward. Because of lensing, the area around Sagittarius A-star becomes more than a simple location. It becomes a stage where the geometry of the universe performs openly. The arcs of light you might see in simulations or real observations are not illusions. They're the paths taken by photons as they slide along the curved surface of space, tracing out the unseen gravitational landscape. It is one of nature's most elegant demonstrations. Gravity doesn't just pull on matter, it pulls on light itself. Albert Einstein captured the essence of this when he said, "Gravity bends light." At the time, the idea sounded almost playful, almost poetic, but the universe took the statement literally. What Einstein predicted on paper now appears as glowing rings in telescopic images. And nowhere in the Milky Way is that bending as dramatic or as instructive as it is near Sagittarius A. The lensing effect doesn't just showcase beauty, it provides information. The brightness, the curve, the timing of lensed light all reveal details about the black hole's mass, spin, and environment. As scientists study these features, they peel back another layer of mystery, learning how material moves near the event horizon and how gravity sculpts every motion in that region. You can think of lensing as the universe giving you a gift, the ability to look behind the curtain without lifting it. A natural telescope built not from mirrors and metal, but from the shape of space itself. Space itself is the telescope. And with this strange magnification, Sagittarius A becomes more than a quiet dark sphere at the center of the galaxy. It becomes a window, a lens, a demonstration of the cosmic structure holding everything together. Now that we understand its hunger, its pulse, and its shadow, what does Sagittarius A mean for us? When you look at the Milky Way tonight, with its gentle spiral arms drifting outward like the petals of a slowly turning flower, it's easy to imagine stability, balance, calm. But the galaxy you see now is not the galaxy it has always been. And deep beneath that calm surface lies a story written in heat, in gravity, and in eruptions so vast they reshape the structure of everything around them. To understand what the Milky Way truly is, you have to understand what Sagittarius A has done, not just today, but across millions of years. Supermassive black holes influence their galaxies in more ways than one. They don't just sit at the center like cosmic anchors. They shape how their galaxies grow, evolve, and breathe. The Milky Way is no exception. Sagittarius A, has been quietly, steadily affecting the galaxy's life cycle since long before Earth formed. Start with star formation. Gas clouds drifting through the inner regions of the Milky Way are constantly being pulled, compressed, heated, and stretched by the gravity around the galactic center. When Sagittarius A-star is active, when it feeds, even gently, the energy released can push gas outward, halting or slowing the birth of new stars in certain regions. In quieter times, like the present, the gas settles and star formation resumes at a measured pace. The black hole acts as a regulator, a kind of cosmic heartbeat guiding when stars are born and when the galaxy rests. Sagittarius A has also helped sculpt the galaxy's bar, that elongated central structure of stars and gas that runs through the bulge. Bars act like conveyor belts, dragging material inward over long periods. This inward flow can feed the black hole, and in return, the energy from the black hole can shape the bar's stability and length. Gravity, radiation, and motion all weave together into a feedback loop that has defined the Milky Way's inner architecture. Then there's the distribution of heavy elements, the metals forged inside stars. Over billions of years, material has migrated toward the center, stirred and redistributed by the gravitational forces surrounding Sagittarius A. The mixing of these elements influences everything from the color of stars near the core to the chemistry of the gas from which new stars form. Even the rotation of the bulge, the slow, graceful spin of the central region, is shaped by the mass and presence of the supermassive black hole anchoring it. Although Sagittarius A is quiet today, evidence suggests it was far more active in the past. About 6 million years ago, something happened near the galactic center. Something energetic enough to send twin lobes of high-energy emission bursting outward above and below the Milky Way. These are known as the Fermi bubbles, towering structures stretching tens of thousands of light years. Whatever caused them, it was powerful, rapid, and unmistakably tied to the central black hole. Perhaps Sagittarius A consumed a large cloud of gas, producing jets or winds that carved those enormous cavities into space. Whatever the mechanism, the impact was enormous. Astrophysicist Tansu Dalen described the Fermi bubbles as the ghost of the galaxy's past, and it is a fitting description. They are relics, vast, slowly fading memories of a time when Sagittarius A roared instead of whispered. Standing on Earth today, under a calm night sky, it is almost impossible to imagine the Milky Way burning with that kind of intensity. But those bubbles are proof. The galaxy was once shaped by forces far more dramatic than anything we witness now. When you consider all these pieces, the regulated star formation, the shaped bar, the redistributed metals, the echoes of ancient outbursts, a new picture of the Milky Way emerges. Our galaxy's peace may be the afterglow of ancient violence. The stillness you see now is not the absence of activity. It is the outcome of cycles that played out over millions of years. Quiet does not mean empty. Calm does not mean simple. And Sagittarius A sits at the center of all of it. Not as a tyrant, not as a destroyer, but as a stabilizing force, a counterweight, a gravitational spine holding the entire structure together. Without a supermassive black hole at its heart, the Milky Way's shape, motion, and history could have been entirely different. So tonight, as you imagine the galaxy as a living system, breathing, shifting, evolving. Remember that its tranquility is earned. It is the calm after storms long past, the serenity of a giant that has already spoken loudly and now rests in a galaxy shaped by storms. Why is the heart so quiet tonight? As you look toward the future of studying Sagittarius A, you can feel something shifting. For the first time in human history, our instruments are powerful enough to approach the very edge of a black hole's shadow. Not as a distant theory, not as a blurred smear of light, but as a place we can observe with growing clarity. The discoveries so far are just the opening chapter. What comes next will change how we see the galaxy, and perhaps how we see ourselves. The next generation of the Event Horizon Telescope is already being built. With more antennas, higher frequencies, and vastly improved sensitivity, it will be able to capture details that the first image of Sagittarius A-star could only hint at. Instead of a blurred, shifting ring, we may soon see the structure of the plasma directly, the patterns, the motion, the heartbeat of the black hole, recorded not as a single frame, but as a sequence. A slow, mesmerizing video of light circling the event horizon. On the ground, giant telescopes are rising. The extremely large telescope in Chile, the giant Magellan telescope, the 30-meter telescope. These enormous mirrors will push infrared astronomy into a new era, offering resolutions so sharp they will track the motions of stars near Sagittarius A with precision measured in micro-arc seconds. The orbits will become clearer, the gravitational effects more defined. Tiny shifts in light and position will reveal the black hole's spin, its exact mass, and the way space-time curls around it. Even more promising are infrared interferometers, networks of telescopes working together as if they were pieces of a single planetary-sized eye. With these instruments, we may one day watch matter spiraling into the black hole in real time, tracing the final journey of particles as they whirl into darkness. Every year, every upgrade brings us closer to the moment when we can witness phenomena that once existed only in equations. This is a time of hopeful wonder, a time when our species stands at the threshold of understanding something profound. Sagittarius A is no longer a hidden object smothered by dust. It is a place we can study, a place we can map, a place whose secrets are finally within reach. As Shep Doeleman said, this is only the beginning. And he is right. Everything we have learned so far is a foundation. The real revelations lie ahead. But for tonight, the galaxy is quiet. As the journey comes to an end, let yourself drift back through the vastness of the Milky Way. Far from the bright lights of Earth, far from noise and motion, the galaxy turns slowly in the dark, a silent wheel suspended in space. Its spiral arms unwind like soft ribbons, each one carrying billions of stars, drifting together in a rhythm, older than anything you can name. From a distance, the entire galaxy feels weightless, peaceful, almost serene. Somewhere deep inside that calm swirl, Sagittarius A sits exactly where it has always been, steady, quiet, and patient. You've traced your way from the dust that once hid it, through the radio whispers that revealed its presence, through the infrared glow that parted the darkness, and through the orbits of stars that proved the truth their light could not show. You followed the lensing, the flares, the strange geometry of space, and the ancient eruptions that shaped the Milky Way long before life ever formed on Earth. Now, in the soft stillness of this moment, the monster at the center feels less like a threat and more like a reminder of how much lies beyond sight, how much remains unknown, and how much beauty can exist in something you cannot touch. It is a presence, a gravity, a quiet heartbeat in the middle of the galaxy. Nothing more, nothing less. Let that calm settle into you, the same calm that now wraps the Milky Way. The storms that once raged around Sagittarius A-star have passed. The flares dim, the dust cools. The stars continue their orbits, unhurried, unafraid. Everything in the galaxy is exactly where it needs to be. And tonight, so are you. You don't need to solve every mystery. You don't need to hold every question. Some things, especially the vast ones, the ancient ones, are meant to be felt, not understood, all at once. You can let the universe be big. You can let it be quiet. You can breathe with it, slowly, gently, letting each thought loosen its grip. Just imagine the Milky Way turning in the dark, its heart steady and silent. Imagine the distance softening every worry, every noise from the day. You are small in the most comforting way. You belong to something enormous, but tonight, that enormity asks nothing from you. No answers, no effort, only rest. Even the monster sleeps, and so can you.